Hello, this is the next video in a playlist that I'm calling Introduction to Mathematical Statistics, and we're in Chapter 3, part of the playlist, which I'm calling Continuous Random Variables. And today's topic is just random variables and probability density functions. So a quick definition of a continuous random variables. Random variable x is continuous if it can assume any value in an interval or intervals of real numbers. The probability that it assumes any specific value is 0. A continuous density, let x be a continuous random variable. The function f of x for x real is called the density function for x if these three properties hold. F of x is greater than or equal to 0 for all x. The integral from negative infinity to infinity of f of x is equal to 1. The probability that x is in between any two values a and b is the definite integral from a to b of f of x. Now really the first two properties are necessary and sufficient conditions for x to be a density. The probability of an event, let x be a continuous random variable. Let a be a subset of the real number line. The probability that a is in that set a, or let that denote the probability that the value of x belongs to the subset a, and it's denoted by this probability that x in a is the integral of all x's in that set a of f of x. The cumulative distribution function, let x be a continuous random variable with density f. The cumulative distribution function, sometimes called the CDF, for x denoted by capital F is defined this way. It's f of x is equal to the probability that x is less than or equal to that little x. And it's the integral from negative infinity to x of f of x dx. That's the probability. Let x be a continuous, theorem 1, let x be a continuous random variable with density f and CDF capital F. Then f of x is equal to the first derivative of the CDF function. And here's a quick little proof of that. The probability that x is less than or equal to little x is the integral from negative infinity to x, f of x dx. You take the antiderivative of little f and you get capital F evaluated at x and minus infinity. You plug those values in. Oh, that should be f of minus infinity. I'll fix that in the hard copy. F of minus infinity is 0. So that's just f of x. But remember that f of x was the antiderivative of f, little f. So if we take the derivative of capital F, which is denoted by f prime of x, that's just little f, right? They're derivatives and antiderivatives of each other. Here's our illustration. Now the code I'll copy and paste into the comments section. It's not important. It's more the plot. So we have a density, and that's the graph here, and it's actually the same density. It's a normal distribution if anyone is interested, but we're not going to, that's really not important now. But if we want to find the probability of event A, so where A is between -2 and 1, so we want to find the probability that x is between -2 and 1, we take the integral from -2 to 1 of f of x dx, and this is it. And so it's the area under this curve represents probability. Now if we want to look at the cumulative distribution function of f of 1, which is the probability that x is between negative infinity and 1, that's the integral from minus infinity to 1 of f of x, and that represents this. It's the area under the curve. Now, this density function up here is called d norm. What I do is I want to integrate it from all possible values. So we're going to integrate d norm from infinity to infinity, and it's equal to 1. So this is a density. Here's an example. Random numbers between 0 and 1. Let x equal the number observed. the random number observed. Now, x is a continuous random variable with density f of x equal to 1. And here's how we show that. If we look at the integral from minus infinity to infinity of f of x, but really the numbers are between 0 and 1, so that's the same as the integral from 0 to 1, because anything outside that, it's 0. Our density is 0. And if we plug in 1 here, and then the antiderivative is x, evaluated at 1 and 0, we get 1. So f of x equal to 1 is a density. The cumulative distribution function for x is f of x equal to x. And we can show that f of x is equal to probability from 0 to little x of f of x, or density. Plug in our density, take the antiderivative, evaluate it at x and 0, and we get x. Now find the probability that x is between 0.2 and 0.5. And notice that we can add equal signs or not, and it doesn't change it, because the probability of any specific point in the continuous case is 0. So those are equal. So the probability that we're between 0.2 and 0.5 is the integral from 0.2 to 0.5 of our density, which is 1. And we could just evaluate it, and then we'd be done. But I want to illustrate a point here. This comes down, and we add and subtract the same quantity. Well, then these two integrals from 0 to 0.2 and 0.2 to 0.5 can be combined into 1. But then these are CDF functions. And then it's 0.5 minus 0.2 is 0.3 is the answer. So whenever you have x being in an interval, you can really take the difference of CDF functions, the CDFs, and come up with the probability. Now here is an R example. Of this specific example, we want to integrate the density of the continuous uniform distribution from 0 to 1, and the density of the uniform goes from 1 to 0, 0 to 1, and it integrates to 1. Now, the probability that we're between two values, 0.2 and 5, is the difference of these CDFs, and the CDF is P uniform. We want 0.5 and below, and our density is from 0 to 1. And here we want it from 0.2 and below, and our density is 0 to 1. And we get 0.3, and that's what we got above. Now we can conduct a simulation. Let's do 2 million replications. So we're going to take a random sample of a uniform distribution from 0 to 1, and we want 2 million reps. So boom, it puts it in this vector. It's now a vector of length 2 million. And we want to find, it has to be greater than 0.2, and it has to be less than 0.5. We want to add up how many times that happens, divide by 2 million, and we get 0.29966, which is really, really close to 0.3. That's it for this video. So just under 9 minutes. Hope you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.